Hello KJR readers, my name is Subin and it's a great honor to share our work with you. I will be presenting our study on predicting hepatic decompensation and death in advanced chronic liver disease patients using deep learning analysis of Gadoxetic acid-enhanced MRI. Compensated advanced chronic liver disease is a spectrum of liver fibrosis with high risk of decompensation proposed by Bumwoo 6 consensus. Hepatic decompensation can lead to increased liver-related mortality, so identifying patients at risk of decompensation and death is important. Decompensated advanced chronic liver disease patients, on the other hand, are patients with current or previous event of decompensation, and prognostic prediction is important in these patients in determining the timing of liver transplantation. The degree of liver enhancement on hepatobiliary phase image reflects hepatocyte uptake function, so liver to spleen signal intensity ratio may be used as an index for functional liver capacity. Also, liver to spleen volume ratio holds potential as a prognostic volumetric index, so we hypothesized that these two indices may be used in risk stratification of ACLD patients. Furthermore, ACLD patients tend to undergo repeated MRI examinations, so longitudinal changes of these indices can be informative. Recent development of deep learning algorithm enabled automated measurement of the two indices, and generation of add-on information using routine MRI was made possible. Therefore, we aimed to measure liver to spleen signal intensity ratio and liver to spleen volume ratio with deep learning analysis of Gadoxetic acid-enhanced hepatobiliary phase images and evaluate the usefulness of these indices and their longitudinal changes in predicting hepatic decompensation and death in ACLD patients. This study retrospectively included patients from a prospectively collected data of HCC surveillance study. Patients with high risk of developing HCC were recruited between November 2011 and August 2012. 1 to 3 rounds of paired ultrasound and Gadoxetic acid-enhanced MRI were performed in each patient at 6 months interval. Of the 407 patients initially enrolled, we only included patients with baseline and 1-year follow-up MRI, and after excluding patients by these exclusion criteria, 280 patients were finally enrolled. 32 patients had no ACLD, 186 patients had compensated ACLD, and 62 patients had decompensated ACLD. After fully automated liver and spleen segmentation using deep learning algorithm implemented in our software, volume and signal intensity data were automatically extracted. Liver to spleen signal intensity ratio and volume ratio, along with longitudinal changes, were calculated. As for the study outcome, we assessed occurrence of hepatic decompensation in compensated ACLD group and liver-related death or liver transplantation event in both groups during the follow-up period. We performed competing risk analysis using fine and gray regression model with competing risk defined as above for each outcome. We then performed multivariable analysis using 2 models, the first using only baseline MRI indices and clinical variables, and second model adding the follow-up MRI indices. Probability of occurrence were demonstrated with cumulative incidence functions after accounting for competing events. This is the baseline patient characteristics of our study. Here we can see that baseline liver to spleen signal intensity ratio and liver to spleen volume ratio are significantly different between three groups, whereas the delta indices referring to the longitudinal changes are not significantly different. In the compensated ACLD group, both baseline liver to spleen signal intensity ratio and volume ratio were independently associated with hepatic decompensation in the baseline model. In the follow-up model, baseline liver to spleen signal intensity ratio and delta index of volume ratio were significant predictors for hepatic decompensation. After applying and combining optimal cutoff values for each baseline index, the patients were stratified into three distinct prognostic subgroups with different cumulative incidence functions of hepatic decompensation. When predetermined cutoff values of plus and minus 13% for delta liver to spleen volume ratio were applied, patients were again stratified into three subgroups with significantly different cumulative incidence functions. On the other hand, only delta liver to spleen volume ratio was the independent predictor of liver-related death or transplantation in compensated ACLD patients. The patient subgroups stratified using plus and minus 13% of delta liver to spleen volume ratio cutoffs showed significantly different cumulative incidence functions. In the decompensated ACLD group, baseline liver to spleen signal intensity ratio in the baseline model and the delta liver to spleen volume ratio in the follow-up model were each independent predictors of liver-related death or transplantation. These are cumulative incidence function graphs stratified by baseline liver to spleen signal intensity ratio and delta liver to spleen volume ratio in predicting liver-related death or transplantation in the compensated ACLD group. Here is a representative case. A 63-year-old male who had compensated ACLD had baseline liver to spleen signal intensity ratio of 1.34 and liver to spleen volume ratio of 2.86. After 1 year, the indices changed as above, and the delta liver to spleen volume ratio was calculated as minus 24.7%. The patient belongs to the intermediate risk group when considering the baseline indices, and when this intermediate risk group is further stratified by delta liver to spleen volume ratio, the patient belongs to the blue line, showing high risk of decompensation. This patient actually developed hepatic decompensation after 25 months and underwent liver transplantation after 14 months later. This is the conclusion of our study. We demonstrated that lower baseline liver to spleen signal intensity ratio and volume ratio were associated with higher risk of decompensation, and a decreased liver to spleen volume ratio during longitudinal follow-up is significantly associated with all liver-related events. Deep learning algorithm enabled automated measurement of these indices, facilitating their use for risk stratification of ACLD patients in clinical practice. Thank you for your attention.